Pretty much then. Good morning, everybody. So I want to talk about disk around binaries and binaries in big disks. These are two different topics that I'm going to explain. So I really have 2.5 topics I want to cover. Okay. So let me begin by talking about circumbinary accretion. So we already have a couple of talks already and discussions in the last 2 days on these topics. But I have the talk ready, so I want to go through some basic things, hopefully still somewhat useful. All right. Okay, this thing, what is this? Try. Turn on. What's subtitle try? Okay, anyway, doesn't matter. All right, so this is the picture we have. There's something here. Should I? All right, what is this? Got it. All right. Okay, this is the basic picture we're familiar with. We have a binary at the center. You have a disk coming from far away, right? And viscous stress, the gas gradually coming in, get disrupted by this central binary, this egg beater or dumbbell at the center, truncated. And then, of course, the gas try to sneak in through accretion streams, eventually accrete onto this 2 mini disk around individual stars or individual black holes. So that's the basic picture, right? Now, this problem has been studied over many decades, right? And obviously I cannot do justice to all these papers, except pointing out this pioneer work by Artimovis Lubo, and also Willie Clay's group had done a lot of work in the past and still ongoing. Willie unfortunately passed away a few months ago. Among all these simulations, there are really 2 kinds, right? And many of the simulations excised the inner cavity for technical reason, right? Truncate the cavity, focusing on the gas in the circumbinary region. And this kind of simulation is useful for some problem, but not always. One has to be careful, of course, for some other problems. And of course, in recent years, there have been several groups developing codes, finite volume code that can cover the whole domain from circumbinary disk, large circumbinary region, going through the accretion stream, eventually going to the individual disk. Okay, so let me quickly summarize some of the key dynamical results as I see them, focusing on short-term variability, long-term variability, and angular momentum transport. So I'm going to talk mostly about our own work, which solves viscous hydrodynamical equations and simple alpha viscosity, simple equation of state. All right, no turbulence, no magnetic field. Now, our work, we really means Diego Menuz, who is now currently at Northwestern, had babies, moving on the job, and transition in Chile, so he's very busy. And also a former student, Ryan Miranda, who has unfortunately left the field. Very good work, but okay. Short-term variability, this is, I think we already heard a bit already, and this is known for some time already. If you have a circular if you have almost circular binary, then the dominant variability in the accretion, it's about 5 times orbital period, right? And this basically is a orbital frequency of gas lump at the inner edge, the truncation radius of the disk, right? So that lump frequency get imprinted on the accretion, right? And this is known for some time. You get this bursted accretion. Now, if you turn on the eccentricity even a little bit, 0.05 or larger, slightly larger, the accretion m dot variability change dramatically, become this. The dominant variability become the orbital period of the binary, because in this case, what happens is that every orbit, the binary at epicenter, it grabs the gas from the inner edge of this truncation, and then that's how your accretion works. All right, so this is so that's short-term variability. Long-term variability, this is a little bit academic, but I like this result. It's interesting. So here is this m dot light curve, right? There are 2 curves here, you can see, right? 2 curves here, red and blue, that correspond to m dot 1 and m dot 2, the accretion rate onto individual black hole, right? They track each other, no big deal. This is an equal mass binary circular orbit. Now, if you turn on the eccentricity, Again, equal mass, right? But the eccentricity, you see this light curve, this is supposed to go, the curve go, this, right? You can see for a long time, the accretion is dominated by m.1, the blue. And then after several hundred orbit, the red become dominant. The accretion become predominantly dominated by m.2. And it's kind of similar, this kind of symmetry breaking. So okay. Right. So this is some, you can imagine some implications. So you could have a completely equal mass binary, and then at given time, you see only accretion onto one object, symmetry breaking. So we now understand what's happening here is that this 200 orbital period really correspond to the precession of the inner region of the disk. So what happened is that the inner region of the disk become coherently eccentric, and they precess, driven by the quadrupole of the binary, right? The precession period roughly it's 200 PB or 200 or 300 PB, okay? And there's some theory behind this. One can try to understand the behavior, okay? And but I'm not going to go through this technical stuff. So then finally, of course, we heard quite a bit already. This angular momentum transfer between the binary and the long-term orbital evolution. Since the 1980s up until 2017, there have been many claims, or based on simulation or just claims, that when you have this accretion under this ecbeater, this makes sense. You have suppressed accretion. That seems make sense, right? And then that the binary will lose angular momentum through Lindblad torque, and that also makes sense because if you have this ecbeater rotate very fast, faster than the gas outside, the gravitational coupling between these fast rotating dumbbell and this gas outside is such that you transfer angular momentum from this dumbbell to the gas outside. So that all makes sense. But we were quite suspicious about this simple reason, right? Basically, you have a gas supply from outside and you suppress the accretion. I mean, how can you keep on going like that? I mean, eventually you want to reach some quasi-steady state, right? And so it's sort of trivial point. And so the first indication that this may not be the case was the work done by Ryan Miranda in his PhD thesis work and published 2017. And what he did, he was using the Pluto code, which is basically cut out the central cavity, so one has to be really careful, right? Okay. So what he did is this very, very carefully designed experiment. You have a large disk from far away, you supply m dot in a constant rate, and then of course the gas gradually spirals in, gradually transport in, eventually enter the cavity, right? If you run this carefully a long time, you reach quasi-steady state such that the time average m dot across the disk is constant, both in time and space when you average it properly, right? And Ryan achieved that. And then once you achieved that, he can calculate the angular momentum transport rate, angular momentum flux across the disk, right? This angular momentum flux across the disk has three pieces, right? The advection piece, due to the fact the gas is coming in, the viscous piece, right? The neighboring element that are rubbing against each other, transport angular momentum. And then you have these central dumbbells sitting there that also affect the torque balance. So if you add them up in quasi-steady state, that should be that global eigenvalue, global m dot, should be the j dot onto the binary, right? And this is you look at this red line. This is this red line. That's what it is. It's a constant, right? In space and time, right? And that value j dot, global j dot is equal proportion to m dot times this value 0.7 a squared omega b. AB is the binary separation. Omega b is the orbital frequency of the binary. Okay. Now, of course, definitive proof of this require really, if you think about the global problem, j dot. The j dot really is determined by this, what's happening in the inner region of the, how this interact with the physics of inner region, right? So to really prove this, one has to do the simulation that covers not just cut out the cavity, but simulate the whole thing, right? And that was That was Diego did actually first in 2016, but we eventually tried to evaluate the torque carefully and they eventually published in 2019. With this complete simulation, one can directly compute the torque on the binary, right? And that includes gravitational torque on all the gas on the binary, on the individual, on the binary, and also accretion torque. You add them up, you can calculate directly. Just a little bit technical note, and I actually think it's preferred to use passive binary, meaning that you prescribe the motion of the binary, not try to evolve the binary motion dynamically, because that gives you a lot of control, scaling, all the kind of things. And I don't think if you do it carefully, I don't think there's a problem with the Newton's third law. Another technical point is we recently, in a different context, thought about this problem again, and I now think we should have added this pressure term. Basically, when you look at momentum flux on across certain region, the momentum flux includes not just rho v square. You have a pressure term that should have been added. Okay, and okay. Anyway, if you compute the torque directly, you see like m dot. You can see it's very dynamically, chaotic, right? And the j dot, if you compute, is also heavily varying. It can fluctuate a lot. Actually, you can see this curve, this thing, right? And if you do time average, you get this global value, which is constant, right? And this is a global eigenvalue. J L naught is big. J dot divided m dot. It's a value which is equal to this thing, right? So angular momentum received by the binary per unit accreted mass. It's a positive number, so we are pretty confident this is the case because you have two ways to compute this thing, right? One, direct computation, another calculating the torque, calculate the angular momentum flux across the disk. They're consistent, you get a global balance. So it's for me, it's very convincing. Okay, don't need, right? All right, and just recap, the flow is highly dynamical, right? But of course, the fact is very dynamical. It reaches quasi steady state such that the average m dot it's balanced and the average j dot is balanced. Okay, average angular momentum transport rate is balanced, and the binary receives angular momentum, and this has been of course proved by different groups now, and everybody agree now. And of course, the implication is that of course the binary will expand orbital because it receives so much angular momentum that can overcome the mass equation. The orbit can still expand. All right. What about eccentric binaries? This is actually the reason for the delay. We published this result because at least when that time we couldn't find a way to try to, in this passive approach, how do you compute the E dot, eccentricity dot? Right? Now, to calculate orbit evolution, you need both J dot and the energy dot, right? Now, energy dot, what kind of energy you're talking about? The mass is changing, so hard to think about. But once you did it, it's actually very simple. Sort of, it's a well-defined scheme. You can do these things, so we can calculate. So we did not have a lot of computer power. So Diego did only a few cases. Zero eccentricity E dot is consistent with zero. Small eccentricity 0.1 is a positive E dot, and then if you're the larger eccentricity, it's negative, right? So they're not monotonic. And this has been, and of course, there's a nice paper by Jonathan Drake, did this systematically cover much larger grid points, and you see this non-monotonic behavior of eccentricity evolution. There's the eccentricity attractor at about 0.4, and that we heard about yesterday. And there's an implication for the in different region of this, the A dot may be different, have different sign that we heard about a little bit yesterday also. All right, so that's the sort of equal mass binary. What about unequal mass? Well, this is okay. Again, it's an old result already known some time ago. I could find Matthew Bates' paper 2000. The low mass component accrete more, right? It's extended more from the central mass, and so they grab more mass from the disk, in that region of the disk. In this paper, we had a fitting formula for the preferential mass accretion rate, right? And low mass accrete more. The variability is also of interest, right? And if you have zero eccentricity, I mentioned before, the dominant variability frequency is 1/5 of the orbital frequency, right? But if you go to low mass ratio, the dominant variability become omega B, orbital frequency, this is of interest because it's if you care about variability, this is maybe of interest. And angular momentum transfer, you can do these things, right? As a function of accretion rate, mass ratio, and right. If you go to extreme mass ratio, the orbital expansion turns into orbital decay, and you can keep doing. You can do more parameters. Space study, and there's a nice paper by Sweek et al. And on the archive just recently. Okay, so just recap. In quasi-steady state, comparable mass binary can, but maybe not always, expand while accreting from the circumbinary disk. Now, the natural question is: the binary decay possible? Well, and this is in the context both in the AGN context, binary black hole, and the star formation context. My answer always maybe and yes, right? We heard the first, for example, we heard a nice talk by Chris that if you have a thin disk, which may be more relevant for AGNs, you could get orbital decay. And I have slight minor concern about this steady state issue. And the torus, well, the torus is the same as the fine mass feeding, constant feed the disk. Although we have done these similar things. Another possibility, of course, is that if you have a massive disk, in particular, if the local mass of the disk in the region of the binary is larger than the secondary mass, right? Then you have, the problem is very different, right? In that case, you have essentially like a type 2 migration like planet. In that case, I don't think there's any problem for orbital decay. And this is perhaps what's happening in the context of star formation that we heard, I think, nice discussion from Maxwell more the other day. And the third thing I think probably is important is you can really get a sort of a suppressed accretion because you have this dumbbell at the center that, prevent the accretion by driving outflows. But that has not been demonstrated. It's possible that that you really can, this is an important effect. And of course, there will be a lot of caveats that people, more competent people like Sasha, people like Scott Noble and Julian and Roger, they can worry about equational state cooling and all the kind of field turbulence, that kind of things. It's okay. So that's okay. So that's the first part of the talk. All right. So all right. So far I've talked about coplanar. Everything's coplanar disk. You can naturally ask what happened when the misaligned disk, the binary is here, gas coming in from different direction. That can occur very naturally especially in the star formation context, right? So I have a chunk of slides because I had them, and I'm going to leave to Steve Rubel. Hopefully you'll talk about these things, right? And except I just want to highlight this. For me, it's a very beautiful result, surprising result, because in astrophysics, we always like surprises. Otherwise, it's kind of boring, right? And this is a surprising discovery by numerical simulations that by Rebecca, Martin, and Rubel that if you have a disk around the eccentric binary, there's a possibility that the disk can evolve towards a polar alignment. Basically the disk is perpendicular to the orbital plane of the binary, and that's very interesting. So I'm sure Steve will talk about it. So former student, JJ Zanazi did a nice theoretical analysis of this, which I like, and so it's very nice. Okay, and this afternoon we may have a discussion. I hope Ian Zakala he had some intriguing puzzle, at least for me, on this kind of thing. So I'm looking forward to discussion on this. I don't know what's the answer to this. It's very interesting. Now let me move on to the second part of my talk, binary in the big disks. Right. So binary in the AGN disk. We heard a little bit already yesterday by Savik that in the recent years there have been a lot of interest in considering the possibilities that the binary merger, double black hole merger detected by LIGO may come from AGN disk in this environment. It's a very attractive, this sort of notion that deserves study. Okay, and many people sort of have said or just commented in their papers that, this is like a circumbinary equation, right? Because you have this binary embedded in this big disk. It grabs gas from the big disk, then you have a circumbinary disk, and then eventually, just like the circumbinary equation I just talked about, it's like a circumbinary equation. Therefore, you can adapt the result from circumbinary equation onto this problem. I'm not sure about that thing. It's actually not clear for me, and because you have all these shocks when you put this thing, even a single body, the disk, all kinds of shocks that can produce that disturb the flows. It's actually quite complicated. In any case, we would care about what's m dot onto the binary, right? And you want to know the orbital evolution. You want to know what's m dot. So there have been only limited study on this. The pioneer work by Baruto et al. And 10 years ago, basically, right? They could not do this, of course, to the whole real AGN disk. Instead, they were doing this mass ratio Q equal to 10⁻³ which is the mass ratio between the binary and the supermassive black hole, 10⁻³. You want to resolve this thing, so you want to make a more modest mass ratio. And they find that the orbit of the binary decays, right? And then there's the recent work by Hui Li's group in Los Alamos pointing out that this may be a numerical artifact. If you try to do the gravity carefully, you get opposite sign, and that may be dependence on the temperature of the disk, right? And I think we're going to hear, I hope we're going to hear about this afternoon or later today. Here's what we're doing. We really means predominantly means Ruxin Li, the postdoc at Cornell. He's super careful person. Okay, so we had one paper sort of posted recently, and so what we are doing is a local sharing box. So this is a perfect sharing box problem where you basically go to the binary frame, center mass frame of the binary, moving around the supermassive black holes. You're in the rotating frame, right? You sit on the center mass binary. You see a flow coming in, right? Right, and then you want to know what's going to happen to the binary, right? And so Ruxin is using Sina with a Nash refinement so that you can resolve the flow between the components to 250 cells. So it's a high resolution, and we can essentially have zero softening gravity, basically. So Ruxin, I hope, yeah, I thought he's actually online, so you can ask all the difficult questions. Because I'm really a pseudo numericist, really not numericist, right? So, all right. So, but before I talk about the result, let's just think about what are the scale of the problem, right? The length scale of the problem and the velocity scale of the problem, right? Right. So you can think about obviously the orbital separation of the binary is relevant. AB is relevant. And the Bondi radius, like GM binary divided by the sound speed of the background gas, that's relevant, the Bondi radius. And the Hill radius, RH, is also relevant, which is the radius within which, right, the gravity of the binary become important, more important compared to the tidal gravity from the supermassive black hole. And then of course, the overall scale height of the AGN disk is also relevant. So these are the relevant length scale of the problem. The velocity scale of the problem you can also think about, right? The orbital speed of the binary, that's relevant. The sound speed of the background gas is relevant. And importantly, the velocity shear, you sit on the center of the binary and then you see a velocity shear. How much shear you have across the binary, that's also relevant. So it seems you have all these different things. Fortunately, if you actually evaluate it, only two-dimensionless number matters, right? Really, okay? You don't need to all these things, just like only two-dimensional ratio matters. The first one, Q over H cubed. The Q is the mass ratio of the binary, between the binary and the supermassive black hole. Little h, it's basically scale height of the background disk, right? So it's related to the temperature. So this is one parameter. For people doing planet context, this ratio is basically mass divided by thermal mass. If without probably familiar with this, some other people are familiar with this kind of ratio, okay? The other ratio, important ratio, of course, it's basically the size of the binary relative to the Hill radius, right? It's RH divided by AB, it's called lambda. And that, of course, should be greater than a few times, at least a few, in order for the binary to not be disrupted, right? So there are all these things, but actually only two are relevant. And so the problem really depends on these two ratios, in addition to all the other obvious parameters like mass ratio between the binary and eccentricity of the binary, and then the equation of state. Well, if we only do simple equation of state, isothermal or some gamma law equation of state. So in that case, it's actually a very clean problem. So I like clean problems. So all right. So this is all right. So I think probably the key message I want to convey. I think this problem, many people will be exploring this problem. I think many people will probably do this better than us, faster than us, right? But I hope that, because people, when we look at the literature, people usually do this, then do that, and it's hard to compare what's doing what, right? So I hope people sort of try to do the scaled way so that you can actually explore this systematically. And many years ago, I received a lesson from Salpeter, who only believed dimensionless number when he's a physicist. But anyway, that's a different story. Anyway, so Rixin and have begun to systematically explore these parameters space, and in the submitted paper, we actually have only a little bit of this thing, but more will be coming. But all right, so let me just instead of review the result and just quickly just highlight a little bit. Okay, right, the flow structure is complicated. You have at least 2 pairs of shocks, bow shock, and each black hole generates spiral shocks. 5 minutes. Okay, thank you. Okay, and so the shock collide with each other. A very complicated flow structure, and we treat the black hole as the absorbing sphere with a sync radius, right? We can and so every time a gas element collides with that sync sphere, it's become part of the black hole. So from that you can calculate m dot, and you can also calculate the force on each black hole, which should include gravity and accretion and pressure. All the things can be done carefully, and from which you can determine a dot and eccentricity dot. Here is a typical result. You should not take this as a sort of universal thing, it's just, right? The m dot onto the binary can be very much suppressed compared to the naive expectation boundary Hoyle-Letterton equation. Even if you try to be clever, try to say, well, this shear is some kind of velocity, so you put it in the boundary formula, and that's still suppressed because the flow has all this shock structure. And also depends on the sync radius, at least in the way we are doing it, with no viscosity. The m dot is actually not well defined, depending on the size of the black hole, size of the sync radius. Okay? And this is actually a typical feature when you have this large shear flow. And here's the L dot, the specific argument received by the binary per unit of created mass is negative, right? Negative in the basically nu b VBAB is basically VB is the orbital velocity of the binary, AB is the binary separation, right? So it's negative. So as a result, the orbit decays, right? At least for this set of parameters. So Rixin has explored dependence on eccentricity, its dependence on the mass ratio between the binaries. So there's some result you can look at. But there'll be more parameter exploration. I think other people may also be doing this thing. So I don't have a good summary here, except just say I think this is interesting. For me, it's a very interesting, clean problem. Maybe clean, maybe of course once you add complications, like magnetic field become very complicated. The scaling, I think, is important. And all right, so 2D versus 3D, local versus global, and all the viscosity, all these things remain to be explored. Okay. Now let me just next 4 minutes, 3 minutes talk about the last topic, which may be the best, maybe the most interesting one for me. Okay. This concerns the formation of merging black hole binary in the AGN disks. Now we heard about many people are exploring this problem, have written extensively on these topics. There are a lot of physical processes happening in these things, right? And all kind of things. There are a lot of papers, quite a few papers, right? Now, one question of interest is where this binary come from, in AGN disk come from. There are several possibilities that have been discussed. One, of course, the binary could just form in this AGN disk. The AGN disk at 1 parsec scale also is gravitationally unstable. So you have fragmentation and therefore form binary. That's expected. Although the binary form there is actually not clear, has the right property to merge. Okay. And we heard that yesterday from Savik that you could have binary captured from nuclear star cluster get captured, and that some people discussed. All right, okay. And then the final possibility that also been mentioned is what I want to talk about. Suppose you have a single black hole, in the AGN disk, and how they can become a binary. Okay. So this is a paper we just posted a few days ago, and the main author is over here, Jialu Li, is a graduate student. Okay, so here's the problem. It's actually, here's the problem I want to talk about. This is well defined. Suppose you have two little black holes, M1, M2, on a closely packed, nearly circular, near coplanar orbit around supermassive black hole, right? They could be brought together by migration, right? They come close. Now it's well known if they're too close, namely if the A1 minus A2 separation in semi-major axis is less than about 3 times the mutual heel radius, the orbit configuration is dynamically unstable, right? Dynamically unstable. The question is, what's going to happen to the two black holes when you put them in this unstable configuration, right? So of course, the first question you will jump to your mind, what about the gas is complicated? So I'm going to ignore gas for now, for the next 2 minutes. Don't ask about the gas, ignore gas for now, just vacuum, right? Now this problem in the case of two planets on an orbit around the star, this has been well studied. Well, actually only recently studied carefully in my opinion. And the two outcomes, the first one is one of the planet will be ejected. Right? This is actually how you form out cloud, basically. Right? Another outcome is the planet will have collisions. Right? Now, in the case of two black holes around the supermassive black hole, the mass ratio is much more extreme. In that case, you can show that ejection is impossible. It takes forever to happen. So the question then is, you have this unstable black hole in this orbit. Unstable orbit, they just wander around sort of in the chaotic orbit, and they are going to experience recurring close encounters and separate, close encounter means the separation is less than the boundary, than the heel radius. And what's going to happen to them, right? And here it's the sort of simulation Jialu did, right? So the top, just look at the top curve, top panel, showing the mini curve, but each curve represents one realization of this problem where you just count as a function of time how many close encounters these two little black holes will experience, right? So initially start with 0, you can see the time goes down more close encounter, right? So on average, in solid line, you see that at about 10 to the 5 orbital period, you get about 160 or so close encounters. So the recurring close encounters. The bottom panel, 3E2, close encounter of the second kind, so means that close encounter where the separation becomes less than 1% of the heel radius. It's much more rare, of course, infrequent. You can see this thing, right? In 10 to the 5 orbit, you only have, on average, a few such a very close encounter. And all these encounters, when they are during close encounter, they actually temporarily bound. If you calculate with a very close encounter, you can actually calculate the binding energy. They are negative. They are temporary bound. The typical theory, this is the separation of the binary, the semi-major axis of the transient binary, is about heel radius. That's not surprising. They come from this heel radius, right? But unfortunately, this binary, they're all short-lived. Almost all of them are short-lived. They immediately get destroyed by the tidal force from the supermassive black hole. Okay, so that's just because they come together, just because they temporarily bound, does not mean they're permanent. Okay. However, for very close encounter, very close, which is very rare, the gravitation radiation between this little binary, transient binary, can be important. That can suck away the orbital energy. Then they can be captured into a permanent binary. Okay, and now how close is close? Well, if you estimate it, it's 10 to the minus 4 heel radius. So that means if you want this to be important, you have to be rely on this very occasional, very rare event where they come very close. They can be captured. Now the natural question is how often this can happen. Well, so I talked about close encounter CE2, 10 to the minus 2. That's not close enough. So you say, well, you can do this, just do more. And of course, I think in this case, even when you have a very good student, very hardworking student, it's not wise. It's not wise to do this thing because, it's a very rare thing, right? Fortunately, I'm running out of time. You can actually think about the problem. I call this a relative loss cone problem, basically. It's like we heard about loss cone, but this is a relative loss cone problem. You can actually do this in a little bit clever way. And here's the result. I'll skip the detail, right? And this is the average capture rate as a function of time, right? Depending on capture radius. So, right? From this, you find that it basically on average takes about 10 to the 8 orbit. So many orbit in order to have such a very, very, very close encounter in order for this binary to be captured, okay? Become a merging binary, okay? And if that happens, That captured binary actually has very nice property. You can easily predict, and they will enter, they'll be captured at typically 1.4 hertz, depending a little bit on the parameters. Once it's captured, it will decay, will merge within a field orbit, and will enter LIGO band with very large eccentricity, okay? And, all right, and the final thing, Dan, sorry, people will ask, the final thing, what about gas effect? Well, the answer is the honest answer. I don't know. We don't know, right? It's complicated, okay? But you can try to do this naive thing, putting some frictional force, that kind of mimics, hopefully mimic the gas effect. But you should not trust this too much because it's really right. And the answer is that the gas does not necessarily help. It's actually sometimes actually negative. It does not help at all. It actually diminishes the cross rate because the frictional force actually acting on this unstable object actually makes the object separate and then become stable. Okay, so it does not necessarily help. Okay, so this is a nice problem. Whether this is realized, this is sort of happened in nature, I don't know, but it's an interesting problem. Okay, thank you. Let's stop.
That was great. So do we have any questions or discussion? Maybe some PhD students or students in the audience will start us off. Well, while you're thinking, Caitlin has a question.
Okay, I have so many questions, but I'll stick to one on this last point. So you mentioned 2 types of outcomes for this scattering, but there's 3. The third is collisions with the central object.
Yeah.
So it's well known in the planetary literature that you're right, that the first 2 are much more common, ejection or planet-planet collision. That's in large part because the planet radius is larger compared to the Hill radius than in the black hole case. But in this case, if it's taking you 10 to the 8 orbits to get a capture, usually I would expect you to be much more likely to have pumped the eccentricity up to where either tidal encounters with the black hole matter or a straight up collision. So did you include that in the simulations, or why does it happen?
Jialu can answer. Does not happen very often. Does not happen. You're right. For planet, there's the branching ratio. There's this paper by Jialu when he was a planetary dynamicist. I'm also pseudo planetary scientist these days. Yeah, there's this third outcome. You can have a collide with the star. That's indeed the case.
Okay. Yeah. Thank you for the question. So this 10 to the 8 is, as Don just said, to simulate actually this long and really seeing the black hole mergers just do by brute force n-body simulation. It's going to be very challenging. So this 10 to the 8 is sort of based on our distribution and a bunch of extrapolations that we did. So we got that. For our simulation, we do allow collision with a black hole. But as we said earlier, our simulations stop at around 10 to the 5 orbits. In that case, that collision with a supermassive black hole did not happen. But if that happened, we'll be able to catch it in the simulations.
Right. And what about like other, tidal effects with the black hole or things like that? Because there's lots of things that happen before you actually enter the event horizon, right?
The black hole, the O3 of the black hole, O3 appointments. No tidal effect.
Okay.
Thank you. Response to...
it's sort of related, and it's more or less on Jerry's
stuff.
We'll
go to the please go ahead.
Okay, cool. Excellent talk, Dong. That was super interesting. On the last point, so I was just chatting with Charu earlier, it would be really interesting to see what happens if you put the Hill sphere further out in the disk, where basically the tidal shear is less and the physical size of the Hill sphere is larger. And you'd also expect more objects, right? Right. So,
this is scale free. The problem we did is the scale. You can scale this. So
right.
You can do the scale, populate scale this.
Right. The population of objects in the disk, you'd expect the number to go up as R squared, right? And the tidal shear across the Hill sphere is going to be less, right? So as you go further out, you're more likely to have some close.
No, the tidal effect is basically, I'm not sure. The Hill radius, the very definition, the Hill radius, it's essentially the tidal radius, right? It's a scale. You can't scale this problem. So I always, right? It's true you go to far, but it's scaled.
You're not taking a point to the disk.
Yeah, that's right.
Okay, all right.
All right. We have Haiyang Wang on Zoom. Please go ahead.
Oh, hi. I mostly have a question for Xin. Since, as you know, the same term, I remember you used in your paper is something like a vacuum condition that extracts all the materials inside some sink radius. Did you try other same terms? And does that affect the results significantly?
Okay, so for me, okay, we're doing this technical aspect numerical simulation. So each black hole is a absorbing sphere. Every time a gas element touch it, it becomes part of the black hole. So when you do that, the gas, you don't want to try to calculate the gas of this incoming already absorbed gas interacting with the black hole, original black hole. That would lead to this third law problems. But if you do it consistently, it's okay, completely okay. So I'm not sure I understand the question, but this is, for me, it's a very well-defined procedure. Okay, and I never understood the other way of doing it. Sort of that has created some controversy. I don't understand it. But for me, this is the sort of most natural way.
Yes, but sinc cell is actually much larger than this.
Perhaps, yeah, I don't. Yeah.
Okay. We only choose. We just choose the vacuum in the boundary condition. We did not try other sink treatment.
Yeah.
Oh, okay, many thanks. I have actually another question, which is, Yaping Li, his paper is mostly using this locally isothermal condition, and your paper is using somehow like adiabatic gamma law condition.
Yes, we use gamma law equation state. I did not have a lot of room you can explore this thing. The little result I showed is for gamma equal to 5/3, close to 5/3. But then I think Rishin is busy running things. There's some result for other equation state.
So my question is actually.
So we have a question now in the audience. If you introduce yourself.
Hi, I'm Sierra Dodd. Fantastic talk. I was wondering if you had thought much about the inferred rates given this 10 to the 8 orbits.
Oh yes, I prepared on the plane, but I find I'm very timid on the sort of environmental science. Sort of a lot of I did that little estimate. If you assume each AGN has one pair of such things, it's a little black hole, right? And you look at the population of AGN to the best of my knowledge, okay? I find, right, each AGN has one pair of these things happening. You get rate 1 per gigaparsec cube per year, right? Which is quite respectable, okay? So, right? So now you can imagine all kinds of other things that could happen, yeah, all right? But this is a tentative. I'm not sure even worth publishing. So but my experience is, people, when you don't publish rate, you don't care about your paper, but usually the rate is, for me, mostly it's just, it's completely unreliable a lot of times. So for me, at least, sorry, that's my limitation. Just, right. Yeah.
So we have a question from Roman.
Hi, Dong, nice talk. So in this last part of the talk, when you were talking about the gas effects, how were you treating them when the sort of your particles were well separated?
Oh yes, we didn't do anything sophisticated. We just, this is many people try this kind of frictional force. So you can look at it here. The first kind is just friction, where the force on each black hole is equal to minus V minus VK. So VK is a Keplerian flow of the background disk, right? V is the velocity of the black hole. It's just a frictional force.
There was a friction, there was a gas friction outside of the, the moment of encounter, effectively, right?
Sure, they're all here. They all just, you can.
That would be damping the eccentricity. Or...
Yeah, this one, yeah, exactly. This first E drag force has the effect of damp eccentricity.
Right. So in that case, because in a scattering process, you're exciting eccentricity and also separating particles in semi-major axis. Then as this gas drag is damping eccentricity, you actually will be preventing your particles from encountering each other. So that's a well-known effect in.
Sure, yeah. We actually had another paper that hopefully, when Jialu is not attending conference, that is looking at the stability. This is a more well-defined problem. Namely, I told you about this dynamical instability of the orbits, that well-known result, the Hill instability, right? Right, where is it? Right, and that can be modified by some frictional force, right? You can understand it, and but not qualitatively. You can change the number by 50% or so, that kind of thing, but not qualitative way. And again, emphasize that for me, this gas effect is still very much unknown. You should not take this as a Obviously, far from final words at all, right? Because this is just putting some toy force into the thing, hoping to mimic the gas effect, right? And what I'm saying is that it's not necessarily help, does not necessarily help. It actually sometimes, it's actually opposite effect, all right?
Okay, we have time for 2 more from Mark and Savik.
Yeah, so I not to break the beauty of the 2 parameter sort of distribution, but I was curious about a third, which is the shear rate. Now, for most disks would be Popperian, I imagine, but
which one?
I'm interested
sorry,
in
what topic? What are you talking about? Sorry, I didn't get.
The shear rate in the flows on either side of the binary.
Oh yes, okay, this thing. You mean
which I ask about partially because I know these were 2D sims, but I imagine going to 3D. That kind of mimics the effect of decreasing the shear rate anyways.
Yeah, so this, when I'm talking about a very general thing, I apply for both 3D. These are all the length scale and the velocity scale we can think about, right? V shear, it's the velocity shear across the binary. It's a well-defined thing. If you tell me, the Keplerian disk, in the background disk, the shear of this thing. The point I want to make here, despite all this length scale, the velocity scale, actually 2 things only matters. Yeah, only 2 things matters. So actually, I should simplify the problem. At least when you don't worry about all this other turbulence kind of stuff, right? And it's actually well defined. So yeah, I'm not sure I get your question, but we can talk. Yeah.
Savik Ford. So I have a question. I'm a little bit confused in this scenario when you have a binary, right? You find that the gas effects do shrink the semi-major axis. Yes. But then when you form the binary or when you form a temporarily bound system, yes. Why should it be disrupted? Like why is there a difference between this tendency to shrink versus the other?
Well, the problem is here it's well inside the heliosphere. This binary is well inside the heliosphere. So it's you put in there, and this is a real simulation. And whereas in the other case, you start with binary which is very, very large. It's comparable to the Hill radius. Right, and so as I said, most of the time, 100% of the time, they form temporarily binary bond, but then once they go to epicenter.
But when you say well inside, so like I guess what I'm saying is how much smaller? Like,
lambda at least a few.
It's a few.
At least a few.
But so then you've got encounters where they're like 1/100th of the Hill radius. So shouldn't that be okay to shrink? If it's temporary.
Yeah, we didn't find any case, at least that's, the quality difference is that you're starting out from an unbound system where the, sort of a separation, it's Hill radius.
Yeah.
It's very different from, you start out with something that is much smaller Hill radius.
But if you have something that forms with negative energy, like temporarily negative, and it's at 100th of the Hill radius, then that's the part that I'm like.
Okay, I think the honest answer is the hydrodynamics is complicated. One has to do this kind of things. The frictional force thing, you should take there are people publish this, simulation. Maybe you guys, so many people that cannot keep track, but we should take the grain of salt. I think that's fair, probably. Right? There are uncertainties.
Totally fair.
Thanks again, Don, and thanks for all the great questions.